Welcome to this session. This session of the net ionic reactions is about addition reactions. You may have learned them as composition reactions. They're the same thing. Combination reactions. We've talked about the fact that we have grown-ups that can't get along, right? So it may go by all three names, but I'm really glad you're here. My name is Renee McCormick. I'm with the National Math and Science Initiative, and this particular screen that you're looking at has the practice website for net ionic equations that was developed by a gentleman named David Brooks, who has done a fine job. And he's actually the guy who has also headed up the project to put together Chem Team, which you may have done some work out on Chem Team in your first-year chemistry course. It's geared more toward first-year chemistry than it is AP chemistry, but it is a fine resource. If you're ever needing a tutorial and you can't get to one of these recordings for AP, you could actually start out there and get the basics down. So all you do is you go here and you sign up, and then you can tell the site whether you want to work on just combination reactions, combustion reactions, acid anhydrides, etc., and you can practice to your heart's content. So there are no excuses for not doing well on this question on the AP exam. It's the fastest 15 points. It'll be question 4. It'll be the first thing you face right after they wrench the calculator from your grasp. All right, so let's get at it. This one won't take long because there aren't that many examples. That's a good thing because redox is making up for everything. Redox is just the beast. Once you're through with that, then it's everything else seems rather tame by comparison. So here we have two or more elements or compounds that combine to form a single product. That's what an addition reaction, combination reaction, or composition reaction is really called. A group 1 or 2A metal may combine with a nonmetal to make a salt. So if you take a piece of lithium metal and it's dropped into a container of nitrogen gas, we will make lithium nitride. Nitride, not a common negative ion, but it is a negative ion. So if we go back to that periodic table, you know by now that these items right here all bear a -1 charge, while these a -2. My negative doesn't want to work, and this is a -3. So there's my nitride. You know that oxides -2 and fluorides and all halides are -1 and sulfur's -2. So when you are having nitrogen in that nonmetal position when it's combined with a metal, then it's going to bear a -3 charge and be called nitride. So that may not be something you had a lot of experience with in first year. So it's the N3- ion. So two nonmetals can combine also to form a molecular compound, and the oxidation number of the less electronegative element is often variable depending upon the conditions. So generally, the higher oxidation state of one nonmetal is obtained with reacting with an excess of the other. So if I take something like phosphorus, notice that it's not written as just P. There's P4 and there's P10, etc. So we have different forms of phosphorus, and those are called allotropes when you have different forms. So when you're going to use phosphorus, it's probably a good idea for you to write P4, as a matter of fact. Or you could do P10, but I think P4 is probably more common. And then we would have to balance the equation, of course, and react it with chlorine, and we would make 4 PCl3s. And we could do the same thing with excess chlorine and make PCl5. So that's what this is saying. Generally, the higher oxidation state of one nonmetal is obtained when reacting with an excess of the other. So what's the oxidation state on this P? That would be a +3, and the oxidation state on this P is a +5. So when an element combines with a compound, you can usually just sum everything up, just squish it all together. So PCl3 plus Cl2 yields PCl5. Easy to balance, too. Two compounds combine to form a single product. Sulfur dioxide gas is passed over solid calcium oxide. So we're going to make calcium sulfite out of that. Just squish it all together. Polyatomic ions are your friend, whether you've ever thought that before or not. Then this is a classic. This is actually repeated in the acid-base neutralization section because this is the classic Lewis acid and this is the classic Lewis base. And if you remember ammonia, looks like this. And BF3 is allowed to violate the octet rule on the low side since it's so tiny, again with the periodic table. Here's boron. There it is. It's uber small. So anything in front of carbon does not have to obey the octet rule. So it's quite happy with 3 entities surrounding it. So if these two are going to combine together, we get a coordinate covalent bond where nitrogen is saying, okay, I got this pair of electrons, and not really using them, you know, they're just sitting there. And boron's like, well, I don't have anything to contribute to this bonding situation. I'm out. I'm done. I'm tapped. I don't have any more electrons. So nitrogen generously says, well, we can share my extra pair, and you don't have to contribute to the sharing, you big freeloader. And so we often replace that situation instead of with a normal, I erased half my N. Instead of a normal just bond connection, we often put an arrow on it to say that nitrogen was the donor of the electron pair. It's a coordinate covalent bond. And then a metallic oxide plus carbon dioxide yields a metallic carbonate. Now we can do that the opposite direction too. So I know this sounds like a lot to memorize, but if you'll do addition and decomposition together, fairly close together, you'll see that, well, I'm just going one direction, in the forward direction for one and the reverse direction for the other. So really it's not double memory work. It's just, are you going to make this compound, or are you going to destroy and deconstruct this compound? So metal oxides, carbon dioxide yields carbonates. And if you take a metal carbonate and decompose it, you get carbon dioxide and metal oxide. Metal oxide and sulfur dioxide yield metallic sulfite. And if you take sulfite, then you're going to decompose it with a metallic sulfite and make the sulfur dioxide gas and the metallic oxide. So we're talking about a metal and O and a metal and O in both cases, in CO2 versus SO2. So there's a pattern there. So carbonates or sulfites. Carbonate is CO3 2-, sulfite is SO3 2-. So follow the pattern. This is like a set. If you can remember one, you can remember the other one easily. A metallic oxide plus water yields a metallic hydroxide because metallic oxides are acid anhydrides. So if you've already listened to that recording, you already knew that. If you haven't, when you listen to that recording, you'll already know this. And a nonmetallic oxide is a basic anhydride. Anhydride literally translates into without water. And so think about the acids that you can name. It's either a polyatomic ion or a nonmetal that is with the H. And so for these oxyacids, it's the nonmetal oxide that makes the sulfuric acid and the nitric acid. And we can make weak acids as well. I just happen to choose 3 strong ones. And a nonmetallic, I don't know if I said metallic, but nonmetallic oxide. The metallic oxides, if you think about your bases, like NaOH and CaOH2 and things like that, they have a metal in them. So they come from the metal oxide reacting with water. And that's about it. So it's time to just dive in. Are you ready? First one out of the chute is a classic. This is my BF3. As I say, the gases. So you don't have to think about it. You don't have to think about solubility rules. You just write down their formulas. 2 gases are reacting. And we're just going to squish them together like I drew a moment ago. So we make BF3NH3 and call it a day. It is balanced, resists the urge to mess it up. A mixture of solid calcium oxide, so don't even think about it, just write the formula for CaO, and solid, happy dance, I don't have to think about getting the products written down properly. Tetra, prefix meaning 4, phosphorus, deca, prefix meaning 10, oxide is heated. You do not have to draw the little flame above the arrow, but, well, it's a triangle, but I like to think of it as the flame on a Bunsen burner. We're just going to pack this puppy together. So what can we make out of P's, O's, and Ca? Think polyatomic ions. Do you know any polyatomic ions that have Ca in them? Of course not. Do you know any polyatomic ions that have P's and O's in them? Oh yeah, your good buddy phosphate. So start with that. Make phosphate. Put calcium with it. Make a correct formula. Phosphate has a 3- charge. Calcium has a +2. We have 2-3 trick. So I need 3 of the 2's and 2 of the 3's to get to 6. So now, how's that going to work out for me? Well, those O's look most troublesome because there's 11 of them. 10 and 1. So that's going to be a little tricky. So when all else fails and you start looking at this and you go, well, I've got 8 oxygens over here and I have way more over here, then you're going to have to do something here, so give up and double it. So now what you got? You got 16 O's, correct? 4 times 2 is 8, but double it is 16.
So if I put a 6 here for fun, that works actually because 2 times 3 is 6 calciums as well. So I fixed my O's and my calcium all at the same time. So we have a balanced equation. Onward. Solid calcium oxide is exposed to a stream of carbon dioxide gas. See, at least the product parts are easy to write for these. So squish them together. A metal oxide with carbon dioxide makes a metal carbonate. Carbonate is a 2 minus charge, calcium's a 2 plus charge. Happy land of balanced. Solid, calcium oxide again, we're fond of it, is heated in the presence of sulfur trioxide gas, SO3. Well, squish them together. CaSO4. And you're done. It's balanced. Told you you'd like this. Calcium metal. That's just plain old Ca. I like to put an O on it to remind you the oxidation state is 0, but you don't have to do that. It's heated strongly in nitrogen gas. So make a metal with nitrogen. Ca and N, where this is a -3 and this is a +2. It's a 2-3 trick. 3 of the 2s, 2 of the 3s. Get rid of your charges, and there you go. Now balance it. 2 N's on each side, no problem. Calcium's troublesome. 3 here, need a 3 there. Next, excess chlorine gas, that's Cl2, is passed over hot iron filings, not fillings like what's in your teeth if you have any cavities filled, but filings, which just is another way to say a solid. You ever play with those toys when you were little that had like a little plastic kind of guy? Mine was always a bald guy. And then it had little bits of iron in there, and you had a magnet, and you could take the magnet and you could like draw hair on the guy using those little filings. I don't even know if they make those anymore, but I loved them when I was a kid. All right, so we have Cl2 plus just iron metal. Again, you don't have to have the 0. And you've got 2 choices. You can make FeCl2. Because you need to know that iron comes in 2 varieties, +2 and +3. Or you can make FeCl3. It's your call. I go with what's easier to balance. The top one's balanced, so I'd have called that a day. It's already balanced. But if you went with FeCl3, no problem. You're going to have to double this so you can triple that and get to 6. And then you need 2 of these. So it's not hard to balance. It's just that you're in a hurry, so try to keep it simple. All right, powdered, that's a way to say solid, magnesium oxide, +2 metal, -2 oxide, is added to a container of carbon dioxide gas. Well, metal oxides plus carbon dioxide make metal carbonates. And you're fortunate enough to be balanced when that metal is a 2A metal. A piece of lithium metal, okay, also implies a solid, so just write your lithium down, is dropped into a container of nitrogen gas. So we got no worries about solubility rules here to get our products written anyway. So put them together. 2 elements react to do only one thing. Li and N, where N is a -3 and Li is a 1A metal, so it's a +1, so I would need 3 of them. And there we have it. Balance it. Not difficult. Ooh, tricked me. There we go. Still not difficult. I tried to mess it up. All right, what do we have next? Let's go with magnesium metal is burned in nitrogen gas. We like the nitrogen gas thing, huh? So we're going to make Mg and N, where again N is a -3, Mg is a +2, so I need 3 of the 2s and 2 of the 3s. And the N2 worked out nicely, and put a 3 here, and we are balanced. On the real AP exam, remember, even if you get the equation wrong, if you balance what you wrote correctly, you'll be golden. You do need to get something reasonable down on paper that's not just outlandish. Sulfur dioxide gas, sulfur dioxide, passed over solid calcium oxide. Well, put them together. CaSO3 minus 2 ion plus 2 ion, and it's balanced. And then the last one. Samples of boron trichloride gas and ammonia gas. Okay, boron trichloride. Look, that's BF3's cousin. And ammonia. We end the way we began. We're going to just mush these together. BCl3, NH3, but it's still, one more last time, important for you to realize that's a Lewis acid, that's a Lewis base. And what's really going on here, if we draw this out, draw the dang Lewis structure. Pair of electrons there. I can sub out H's or any other halogen for those Cl's. And they would have their complement of unshared pairs around them. But when this bond forms, both electrons are coming from nitrogen. So we write it like that. It's a coordinate covalent bond showing that nitrogen is the donor, boron is the freeloader, not contributing to this bond at all, just mooching electrons off of nitrogen in ammonia, and that's what we make. BCl3, NH3. And that, ladies and gentlemen, does it for addition reactions. Again, I say it's redox that's going to give you the most trouble, but you know what? Even though it's a disproportionate number of examples to work and all, I've got to say that with the new format of this question, the redoxes are a lot easier than what you're going to be doing. So I don't want you to get discouraged when you work and work and work on those redox equations. Get good at this stuff. Get good at everything that's easy. And you know what? You can afford to not worry about the redox ones. There are going to be some multiple choice questions with them, and I'm always trying to improve your multiple choice score, because a lot of the explanations I give you here are not just to hear the sound of my own voice. I'm actually trying to give you those random acts of chemistry that show up in the multiple choice that translate into easy, greasy, quick points for you, instead of having to work a stoichiometry problem with no calculator that has a limiting reactant. So keep at it, keep working hard. We need more scientists and engineers. You know, us old folks are going to retire at some point. We even need more chemistry teachers. And I hope I'm attempting to give you the gift of clarity. I hope it's working out for you. So I greatly appreciate your time and energy, and I hope you have a great rest of your day.